Now we want to begin looking at exponential functions in some detail. Now the basic exponential function, as you've already seen in the overall survey, is y equals b to the x. And I really should write that in terms of function notation as, what have I left out here? Y equals f of x. Slippery there. Equals b to the x. That's a really bad looking f of x. I'll try to correct that a little bit later, but you get the idea. Okay, the defining graph characteristic for any graph defined by this function, or as was the case with power functions, any constant multiple of this function, any function a times b to the x. The defining graph characteristic for any such function is this: for some x displacement represented by this arrow. And this is just how far x is going to change, by how much x is going to change. We'll see that in a minute when I demonstrate. So for some x displacement that I've represented by an arrow, I could represent it algebraically too, but right now we want to stay geometric. So I'm just going to represent the displacement by this arrow. Again, you'll see how. Y doubles whenever x changes by this displacement. So that means if I move this far in the x direction, my y value is going to double. That's all. It's a very simple rule, just as simple as the product function rule, but different than the product function rule. It gives you a function with different characteristics. If something is modeled by a power function, it cannot be modeled by an exponential function, and vice versa. Okay? They are completely different kinds of functions. Okay, so what we want to do is construct a graph. We're going to pick any point not on the x-axis and start. Okay, so I'm going to pick a point. I'm going to pick, let's say, this point right here. Okay, start here. Nothing unique about that starting point. Now I don't have to start in the second quadrant. I could start in the first, I could start in the second, or I could start the third or the fourth quadrant. I could start below the x-axis. And you could actually do that with a power function as well. We didn't do it, but it would be simple enough to do. You would simply get a negative value for the a quantity if you started below the axis. That would be perfectly legitimate. Okay, but applying the rule to this exponential function whose graph we're going to construct, we start here. Now, we let x change by an amount corresponds to, of course, the x value is here, right? So here's our x value. Now we apply this arrow, we change x by this much, and that's going to move us to here. So right there is my change in x. The y value is going to double, so let's see, the y value here was this. We're going to double that. Well, that's pretty easy to do. We're going to move the y value to here, and now we have a second point on our graph. Okay? Okay, well, we can do this again. Okay, let's say we move through the same displacement. Then we're going to end up with this x value. And that's going to double the x value we already have, and that's going to get us all the way up to here. So now we're going to have a graph point here. Now we can apply the y displacement once more. Now let me find a damp place on this eraser so that we can extend the x-axis just a little bit more. And now I can do the same x displacement again, and my y value is going to have to double again. It's going to come up to here. I should probably have extended this arrow as well, but we'll just live with the result for right now. Okay, so there's a pretty good start on our exponential graph. Now, the question is, are there any points to the left of this one? Now, you notice right away, incidentally, that on this graph, unlike the power function, we can go into negative values. Now, some power functions can be defined for negative values of x, but some can't. And we'll deal with that question now that we have good command of the geometry of a power function graph and a good understanding of the way it behaves. Well, okay, are there any points that we can construct to the left here? Well, sure. If we put the same arrow here, we get an x value here, and we understand that the x value here would double in order to give, I'm sorry, that the y value for this x point here would have to double to give us this one. So that means that the y value here has to be half of what it was here. Well, we're used to cutting things in half. That's easy enough. We'll cut that in half, and we'll project over to here. Now we can keep doing this. We cut this in half again and put our arrow here, and now we're going to have a point down here that's pretty close to the x-axis. So what's going to happen if we keep moving to the left? Well, we're going to keep cutting these values in half. Pretty soon, within a couple more divisions, our graph will actually be inside of the line, or the thick line, chalk mark that we've used to represent the line, which is the x-axis. Okay? And now we can connect these points with a smooth curve. And here we have a graph of an exponential function. Okay? So this is a graph of y equals f of x, an exponential function. Now we're going to go on with this and think about a couple more things, one of them being we could have started at any point and done this. And the defining characteristic of the function says that once we've sketched this graph, then if we start at any other point of the graph, again, we have to double if we go through the same x displacement. The same x displacement will double no matter which point there is on the graph. And in a fairly deep sense, that allows us to claim at least, and we'd have to prove it, that this condition is equivalent to this condition. Now that gets fairly deep into the idea of analysis, and we probably won't talk about that anytime real soon. But it's kind of an important idea, so I kind of slip it in here just to get your wheels turning a little bit.